The National Electrical Code, or NEC, does indeed require that the center tap of a secondary winding on a 480 volt to 120/240 volt single-phase transformer must be grounded, specifically when it's utilized to supply both 120 volt and 240 volt loads. This requirement is explicitly stated in NEC section 250.30. This section outlines the grounding requirements for separately derived alternating current systems. A separately derived system is an electrical source, like a transformer, that derives its power independently from the main electrical service. In the context of a 480 volt to 120/240 volt single-phase transformer, the secondary winding functions as a separately derived system providing the 120 volt and 240 volt power. Grounding the center tap of the secondary winding creates a neutral point. This neutral point is essential for several reasons. Firstly, it establishes a stable voltage reference for both the 120 volt and 240 volt circuits. With a grounded neutral, the voltage from either leg of the 240 volt winding to the neutral is 120 volts. This ensures that the 120 volt loads connected between the neutral and either leg receive the correct voltage. Secondly, grounding the center tap provides a low impedance path for fault currents to return to the source. In the event of a ground fault, where a live conductor comes into contact with a grounded surface, the fault current will flow through this low impedance path back to the transformer. This high current flow will then trip the overcurrent protection device, such as a circuit breaker or fuse, quickly disconnecting the faulty circuit and minimizing the risk of electrical shock or fire. Thirdly, grounding helps to limit voltage surges and transient voltages on the system. These surges can be caused by lightning strikes, switching operations, or other electrical disturbances. By providing a path to ground, these surges are diverted away from sensitive equipment, protecting them from damage. NEC section 250.30 details specific requirements for grounding electrode conductor size, grounding electrode system, and bonding connections. The size of the grounding electrode conductor is determined by the size of the transformer secondary conductors. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. Bonding connections are used to connect non-current carrying metal parts, such as equipment enclosures and conduit, to the grounding system, ensuring that they are at the same electrical potential as ground. Economy switching, also sometimes referred to as a single-phase 3-wire system, is a common application where this grounding requirement is crucial. Economy switching is a wiring configuration used with single-phase transformers to provide both 120 volt and 240 volt power from a single 240 volt source. The transformer has a 240 volt primary winding and a 120/240 volt secondary winding with a center tap. The center tap is grounded, creating the neutral point. 120 volt loads are connected between the neutral and either leg of the secondary winding, while 240 volt loads are connected between the two ungrounded legs. This setup is often used in residential and light commercial applications to power both 120 volt appliances and lighting, as well as 240 volt appliances such as electric ranges, water heaters, and air conditioners. The advantage of economy switching is that it allows for the use of a single transformer instead of two separate transformers, reducing the initial cost and space requirements. However, it is important to ensure that the grounded center tap is properly sized and protected from overcurrent. The neutral conductor must be sized to carry the maximum unbalanced load, which is the difference between the current and the two ungrounded legs. In addition, overcurrent protection must be provided in each ungrounded leg of the circuit to protect the transformer and the connected loads from overcurrent conditions. Failure to properly ground the center tap of the secondary winding in an economy switching configuration can result in several problems. Firstly, it can create a floating neutral, where the voltage between either leg and ground is not stable. This can cause 120 volt loads to experience overvoltage or undervoltage conditions, potentially damaging the equipment. Secondly, it can increase the risk of electrical shock. If a ground fault occurs, the fault current may not have a low impedance path to return to the source, increasing the voltage on the grounded surfaces and creating a shock hazard. Thirdly, it can prevent overcurrent protection devices from operating properly. If the fault current cannot return to the source through a low impedance path, the overcurrent protection device may not trip quickly enough, increasing the risk of fire. Therefore, it is essential to follow the NEC requirements for grounding the center tap of the secondary winding in a 480 volt 120/240 volt single-phase transformer when it is used to supply both 120 volt and 240 volt loads. This ensures the safety and reliability of the electrical system and protects people and property from electrical hazards. To further clarify, let's delve deeper into the specific requirements outlined in NEC section 250.30 regarding the grounding of separately derived alternating current systems, focusing on aspects relevant to your 480 volt to 120/240 volt single-phase transformer setup. The code mandates that a grounding electrode system be connected to the separately derived system. This grounding electrode system must adhere to specific guidelines detailed in Part 3 of Article 250 of the NEC. Acceptable grounding electrodes include things like metal underground water pipes, the effectively grounded metal frame of a building or structure, concrete encased electrodes often called G4 grounds, and ground rings. The choice of grounding electrode depends on site conditions and the availability of these electrodes. Section 250.30 also stipulates the requirements for the grounding electrode conductor. The grounding electrode conductor connects the separately derived system's neutral point, which in your case is the center tap of the 120/240 volt secondary, to the grounding electrode. The size of this conductor is determined by Table 250.66 of the NEC, based on the size of the derived phase conductors. It's crucial to select the correct size to ensure a lower impedance path for fault currents. Furthermore, the NEC addresses bonding requirements for separately derived systems. Bonding ensures that all non-current carrying metal parts, such as transformer enclosures, conduit, and equipment grounding conductors, are electrically connected to form a low impedance path for fault current. This is achieved through bonding jumpers and the proper use of listed fittings. The point where the grounding electrode conductor connects to the separately derived system is also critical. For a transformer, this connection is typically made at the neutral point on the secondary winding, meaning the center tap in your scenario. The NEC emphasizes the importance of a solid and reliable connection to ensure effective grounding. Now let's revisit economy switching with a more granular look at its practical implementation and associated safety considerations. In an economy switching arrangement, the grounded center tap serves as the neutral conductor for the 120 volt circuits. Because of this dual role, the neutral conductor must be sized to carry the maximum possible unbalanced load. This means calculating the largest anticipated difference in current between the two 120 volt legs. For instance, if one leg is carrying 15 amps and the other is carrying 5 amps, the neutral conductor must be rated to handle at least 10 amps. Overcurrent protection is another crucial aspect of economy switching. Each ungrounded conductor, meaning the two hot legs of the 240 volt supply, must have overcurrent protection devices, like circuit breakers or fuses, rated to protect the transformer windings and the connected loads. These devices must be sized according to the transformer's ampacity and the load requirements. Additionally, it's vital to ensure that all wiring and connections are properly rated for the voltage and current involved. Using appropriately sized conductors, connectors, and other components is essential for safety and reliability. Regular inspections and maintenance are also important to identify and address any potential issues such as loose connections, damaged wiring, or corroded components. These regular checkups can help prevent electrical hazards and ensure the continued safe operation of the system. Understanding the specific requirements of NEC Section 250.30 and adhering to best practices for economy switching are crucial for ensuring the safe and reliable operation of your 480 volt to 120/240 volt single-phase transformer. Proper grounding, bonding, conductor sizing, and overcurrent protection are all essential elements of a well-designed and properly installed electrical system. Now, to emphasize the importance of grounding within the context of electrical safety, let's examine scenarios where inadequate grounding can lead to dangerous situations. Imagine a situation where the metal chassis of an appliance, such as a washing machine, becomes energized due to a fault in the internal wiring. If the appliance is properly grounded, the fault current will flow through the grounding conductor back to the source, tripping the circuit breaker and quickly disconnecting the power. This prevents anyone who touches the appliance from receiving an electrical shock. However, if the appliance is not grounded, or if the grounding connection is faulty, the metal chassis will remain energized. If someone then touches the appliance while also in contact with a grounded surface, such as a water pipe or damp floor, they will provide a path for the current to flow through their body, resulting in a potentially fatal electrical shock. Similarly, consider a scenario where a damaged wire inside a metal conduit comes into contact with the conduit itself. If the conduit is properly grounded, the fault current will flow through the conduit back to the source, tripping the circuit breaker. This prevents the conduit from becoming energized and posing a shock hazard. But if the conduit is not grounded, or if the grounding connection is poor, the conduit will become energized. Anyone touching the conduit could then receive an electrical shock. These examples highlight the critical role that grounding plays in protecting people from electrical shock hazards. Grounding provides a low-impedance path for fault currents, allowing overcurrent protection devices to quickly disconnect the power and prevent dangerous voltages from appearing on exposed metal surfaces. In addition to protecting against electrical shock, grounding also helps to protect electrical equipment from damage caused by voltage surges and transient voltages. These surges can be caused by lightning strikes, switching operations, or other electrical disturbances. Without proper grounding, these surges can damage sensitive electronic components, leading to equipment failure. Grounding provides a path for these surges to dissipate safely to ground, protecting the equipment from damage. Furthermore, maintaining a proper grounding system is not a one-time task but an ongoing responsibility. Grounding connections can corrode or become loose over time, reducing their effectiveness. Regular inspections and maintenance are essential to ensure that the grounding system remains in good condition and continues to provide the necessary protection. These inspections should include visual checks of grounding conductors and connections, as well as electrical tests to verify the integrity of the grounding path. Any damaged or corroded component should be replaced promptly. In summary, grounding is a fundamental safety practice in electrical systems. It protects people from electrical shock, protects equipment from damage, and helps to ensure the reliable operation of electrical systems. Adhering to the NEC requirements for grounding and maintaining a proper grounding system are essential for electrical safety. Finally, let's address some common misconceptions about grounding. One common misconception is that grounding is only necessary for sensitive electronic equipment. While grounding is certainly important for protecting sensitive electronics from voltage surges, it is also essential for protecting people from electrical shock hazards. Grounding is required for all electrical systems, regardless of the type of equipment being used. Another misconception is that a 3-prong plug automatically provides grounding. While a 3-prong plug does provide a connection to ground, it only works if the outlet is properly grounded. If the outlet is not grounded, the 3-prong plug will not provide any protection against electrical shock. It is important to test outlets to ensure that they are properly grounded. A third misconception is that ground fault circuit interrupters, also known as GFCIs, eliminate the need for grounding. GFCIs are designed to protect people from electrical shock by detecting small imbalances in current flow and quickly disconnecting the power. While GFCIs provide an important layer of protection, they do not eliminate the need for grounding. Grounding provides a low-impedance path for fault currents, allowing GFCIs to operate properly. In fact, GFCIs often rely on a properly grounded system to function as intended. By understanding these common misconceptions about grounding, it becomes clear why it is important to have a qualified electrician install and maintain your electrical system. A qualified electrician will ensure that your system is properly grounded and that all safety measures are in place to protect you and your property from electrical hazards.